Hello, everyone. My name is Lei Zhang, currently a postdoc at the Social, Cognitive, and Affective Neuroscience Unit, University of Vienna. Today, I will be presenting using reinforcement learning models in social neuroscience. Reinforcement learning models have been powerful and helpful in explaining latent trial-by-trial processes in decision neuroscience. In social neuroscience, the investigation with reinforcement learning models have just started. Here are some recent examples to name a few. However, there's still a lack of comprehensive workflow and best practices of using reinforcement learning models in social neuroscience. But before we start, take a second and ask yourself, can you answer the following questions properly with great confidence? How to interpret the learning rate in the Rescorla-Wagner model? What is the optimal learning rate for a simple two-choice task? What is the optimal learning rate for a simple two-choice task with 75-25 reward schedule of 100 trials? How to obtain the optimal learning rate? If you were unsure about at least one of the questions, then this talk is right for you. The most common and widely used reinforcement learning task is the so-called two-armed bandit task, where participants will repeatedly choose between two choice options whose property, for instance, the reward probability, are learned through trial and error. And the goal of the participants is to maximize the overall reward. By breaking down this process, the participants will first predict the value of each choice option and then make their decision accordingly. Then finally, they will learn and update their predictions from the observed outcome. And this process is well illustrated by this paper from 2008. Now that we have the task procedure, namely the choice presentation, action selection, and outcome delivery, we could ask ourselves, what do we know, what can we measure, and what do we want to know? Clearly, we have participants trial by trial, choice, and outcome data from which we can calculate the accuracy for each participant. Eventually, we're interested in the learning algorithm, here the reinforcement learning update. The exact reinforcement learning update I'm presenting here follows the Rescorla-Wagner rule, which quantifies an error-driven learning, or the familiar equation to many of you. The value here is updated through a learning rate-weighted reward prediction error, and here the prediction error is simply the difference between what you actually get and what you expect to get. With this equation or model, what we usually do is to fit the model to the data. Via model fitting, we obtain the learning rate parameter estimate, akin to the procedure of fitting a regression model to obtain the intercept and the slope. But what might seem a bit puzzling is, what does the learning rate actually mean and how to best understand it? We argue that the best way to understand the learning rates, and in fact, the best way to understand any parameter in any model, is to run simulation. The advantage of running a simulation is that first, we know the ground truth, and second, we could see how the model prediction changes as we change the model parameter in small steps. Specific to the Rescorla-Wagner model, the learning rate here is the speed of learning, but it works both for positive and negative outcomes. If the learning rate is large, the model will learn the reward fast, but also the punishment fast. On the contrary, when the learning rate is getting smaller, the model will learn both the reward and punishment in a slower speed. To understand this even deeper, we reorganize the Rescorla-Wagner update rule as an iterative process with respect to the initial value, and we could easily see that the value can be expressed by the cumulative past reward with different weights. When the learning rate is high, the model will weigh the most recent reward highly, everything else in the past close to zero. Yet when the learning rate is low, multiple past trials corresponding reward will contribute to the value computation. The next question is there an optimal learning rate, in the sense that the Rescorla-Wagner model will produce the highest choice accuracy? The simple answer is it hugely depends on the task. As we know, there are at least 3 elements to consider in a task. First, the task structure. Do we have constant reward probability or reversal? And if there is reversal, how often does it happen? Second, the reward schedule or reward probability. And then third, the number of trials. The task here is the combination of all the 3 elements. And as long as the task is settled, we could derive the optimal learning rate, for instance, through simulation. The last question is, what I have said might sound interesting, but how is that related to social neuroscience. As one example, the reinforcement learning task can be easily applied in a social setup where you can learn either for yourself or for a social partner. In this example here, the learning rates for other is higher than the learning rate for self. There is indeed a significant difference, but to accurately interpret it, we need the context of the task. We could identify the optimal learning rates and then compare the self and other learning rates in relation to the optimal learning rates. And only then the modeling analysis is complete and the precise conclusions can be drawn. Given the time limit here, I'm only able to show you one of the best practices. You are more than encouraged to check out our paper for more details. Even nicer, we have set up a GitHub repository. There you could even try to make your own simulation to gain a more comprehensive understanding. Hopefully it will help your own research. Very lastly, I want to thank my lab and my funding, and thank you all for your attention. I'm very much looking forward to chatting with you, no matter if you have a question or not. Thank you.